All right, let's dive into a really cool piece of engineering. It's something that's absolutely everywhere, powering so many things we rely on, but you've probably never even thought about it. We're talking about a true unsung hero of the mechanical world, the external gear pump, and we're going to break down exactly how this thing works.
So, have you ever wondered about that? Think about the engine in your car or giant hydraulic excavators. They all need to move fluids like oil, and not just move them, but move them with incredible force and precision. So, how do they do it? Well, the answer is way more simple and honestly more elegant than you might think.
And here's our answer, the external gear pump. Now, its official name is a positive displacement pump. That sounds kind of technical, but all it really means is that for every single turn of the gears, it moves a very specific fixed amount of fluid. And the way it pulls this off is by using one of the most basic mechanical concepts out there, just a couple of gears meshing together. Okay, so to really get our heads around this, we've got to look at what it's made of. And you'll be pretty surprised, I think, at how a machine this powerful is built from just a few simple parts. So here's the whole team. You've got your driver gear, that's the one hooked up to a motor. Then you have the driven gear, which, you guessed it, is turned by the driver gear. The whole thing sits inside a tough casing. And that casing has two openings, an inlet port for fluid to get in and an outlet port for it to get pushed out. That's pretty much the whole setup. Now, this is the really critical part, because the gears are meshed externally. When one gear spins, the other has no choice but to spin in the exact opposite direction. So if that driver gear is going clockwise, the driven gear has to go anti-clockwise. This opposing motion, this is the secret sauce. It's everything. All right, let's put all those pieces together and see it in action. We're going to follow a drop of oil as it makes its way through the pump. This is where we see that simple spinning turn into a really powerful, directed flow of fluid. So it really happens in three simple steps. First, suction. Over at the inlet, the gear teeth are pulling away from each other. This creates a low-pressure zone, basically a vacuum, that sucks the oil right into the pump. Second, transport. The oil gets trapped in the little pockets between the gear teeth and the outside wall of the casing, and it gets carried around the outside of the gears, not through the middle. And finally, discharge. At the outlet, those gear teeth mesh back together, the space for the oil disappears, and it gets squeezed out with a lot of force. But that last step, the discharge, that's where the magic really happens. That's where all the pressure comes from. So let's zoom in a little bit and see exactly how this simple squeeze can generate so much power. So think about it. The oil is carried along in these little pockets, and then, all of a sudden, that space it's in just vanishes as the gear teeth lock together. Now, oil doesn't like to be compressed, so it's got to go somewhere, right? And the only place for it to go is straight out that discharge port, under pressure. And this quote from our source material just nails it. This isn't some passive flow. It says the teeth do work on the oil, increasing the oil pressure. They are actively, physically forcing that oil out, which is what builds up that pressure. It's a direct transfer of mechanical energy. Okay, so we get the mechanism, but what about performance? You'll find these pumps are almost always designed to spin really, really fast. And, well, there's a very good reason for that. It really just boils down to a super simple concept in fluid dynamics. The faster you spin the gears, the more fluid you're going to move. That's it. You want to pump more oil per minute, you just have to make those gears spin faster. The output, what we call the discharge, is directly proportional to the speed. And this chart just lays it out perfectly. At a low speed, you get a low discharge, but you crank up that speed and boom, the discharge rate just shoots right up. This is exactly why you'll often see these pumps bolted directly to a high-speed motor. There's no need for a gearbox to slow things down. You actually want all that speed. It's built for efficiency. And the design is just so smart. I mean, think about it. You have these metal gears spinning incredibly fast. What stops them from just grinding themselves to bits? Well, if you're pumping oil, the oil itself acts as the lubricant. It's this awesome self-sustaining system, so simple and so effective. Okay, so theory is great, but let's put this into a real-world context. Let's look at a design problem, using some actual specs from the source material we're looking at today. Imagine you're the engineer. Here's your task. You need to design a gear pump that can move 50 liters of engine oil every minute. And it has to deliver that oil at a pressure of 30 bar. By the way, that's over 400 psi. So every single thing we just talked about, The size of the gears, the strength of the casing, the speed of the motor, it all has to be perfectly calculated to hit those targets. And when you solve that complex engineering problem, what's the answer? It's this beautifully elegant solution. At the end of the day, it's just two moving parts spinning inside a case. It's just an amazing example of how a very simple mechanical idea, when engineered smartly, can do some seriously heavy lifting. So, the external gear pump really is one of those hidden heroes, working away all around us. And it kind of makes you wonder, doesn't it? What other brilliantly simple engineering marvels are out there, quietly powering our world that we don't even know exist? Something to think about. Thanks for joining me.